In this video, we're going to cover matrix basics, and in the last video, we covered vector basics. So if you don't feel comfortable with the vector basics, stop this and go rewatch the vector basics because it's going to build off of that. So first off, note that every vector is a special type of matrix, either a column vector or a row vector. So here we have a generic vector A, and I've denoted the elements using a lowercase letter a, and there are m many rows and n many columns, and the way we denote an individual element is by its position on this table. So basically, you can imagine that there's like a grid, so this is like an Excel spreadsheet sort of, and the subscript tells you where in the table that element is. So if I were to say give you element 5, 3, then this would be the element of matrix A that is in the 5th row and 3rd column. So you would go down about here and over here in the 3rd column, and it would be right around there. Okay. So vectors have a nice geometric picture that we can go to and make sense of. They point in space, right? But matrices don't have that same sort of easy geometric picture. They have a geometric picture, it's just more abstract. And in fact, actually, because matrices act on vectors, the best way to think of a matrix is what it does to vectors geometrically. We're not going to cover that though. Okay, so let's describe the size of a few simple matrices. So suppose I give you this matrix 1, -3, 4, 0, 5, -2, and I ask you to tell me the dimension of the matrix. The dimension, this is 2 by 3. Okay, 2 by 3. So you might recall when we were learning the dimensions of vectors, vectors were either 1 by n or n by 1, depending if it was a row or column vector. So in this case, because there's 2 rows and 3 columns, this is a 2 by 3 matrix. Now, if I wanted to specify a specific point, I could use subscripts. So what is element A22? Well, if I go to the 2nd row and the 2nd column, they clearly meet at 5. What about A31? A31. Well, there is no A31, right? Because there isn't a 3rd row. What about A13? Okay, so I have to go to the 1st row and the 3rd column. So this has to be 4. That's 4. Okay, so many of the properties that we had from vectors are going to transfer to matrices as far as their algebraic properties are concerned. So for example, just like you could only add vectors that had the same size, you can only add matrices that have the same size. So if I have this matrix here, and I want to add it to this matrix, I do it pointwise or entry-wise. So 2 plus 7 and 3 plus -1 and 4 plus 0 and 5 plus 8. And then when I evaluate that, I should get 9, 2, 4, and 13. So that's how you add matrices. The next thing we have to cover is scalar multiplication. So just like before, if you multiply a matrix by a scalar, it's just going to go through each entry. So this will be 3 times 2, 3 times 1, 3 times 4, and 3 times 7. So the value is going to end up being 6, 3, 12, and 21. Pretty straightforward stuff. Okay, so you might recall from the vector video that I said you had to add vectors that were the same length, right? So the same can be said for matrices. So if I try to add this matrix and this matrix, I cannot do this, right? The operation is not defined, and so you just don't do it. Okay, it doesn't make sense. Okay, so in your book, we have theorem 10.1. Theorem 10.1 just says that if you add a pair of matrices and then a third matrix, this is going to be the same thing as if you add the second pair first and then add the first one, right? So I can do the addition on A and B and then add C, or I can do B and C and then A, and it's all the same. So a short way to think about this is that I don't have to write the parentheses, assuming, of course, there's no scalar multiple to be distributed through. Another neat fact about matrices is that their addition is commutative. Commutative, so this was associative. Commutative just means that it goes both ways. So you have A plus B, and this is equal to B plus A. And so at this point, you're probably thinking, well, surely that's obvious, because if I think back to my ordinary numbers, then obviously I could add either direction. Well, let's inspect that idea a little closer. So suppose I have two generic matrices. I'm just going to use letters so that the numbers aren't special. They could be anything. Okay, so I'm going to add these two matrices, A and B, and let's think about why the addition is commutative. So the reason it's commutative is because the way we defined addition. We defined it pointwise. So in other words, I'm going to add those two elements, and then I'm going to add these. And these. And then finally, the last set. Okay, so the reason the result works is because if I look at any one of these entries, notice that that right there is just a normal addition. And because it's normal addition, at this point I can swap the order. So over here, I'm going to rewrite that whole thing, and I'm going to swap the order. So I get B11 plus A11 and B12 plus A12 and B21 plus A21 and B22 plus, and I shouldn't have a plus there, A22. Okay, and then just by using the definition that allowed us to go from here to here, right? So that allowed us to use that equal sign. I'm going to now apply it to this equal sign. That's a very big circle. I'm going to apply it to this equal sign, but we're going to unwrap it, and it's going to appear on the other side. Okay, so we can summarize this by saying a plus b is equal to b plus a. Okay, so this is not the case with multiplication, as you will see right now. So let's think about how matrix multiplication is going to be defined. Well, when I multiplied vectors, remember if I had v, say v1, v2, and v3, right? And I had w, right? And w was, say, w1, w2, and w3. How could I multiply these? Well, I did not do w times v, right? We never had that going on, though you can do it, and we'll show how that can be done in just a little bit. But in the first place, when I taught you how to do it, it was with first your row and, sorry, yes, first your row and then your column. So you have v1, v2, v3, and then w1, w2, w3, right? And then what did we do? Well, we multiplied and we added. So this was going to be basically giving us this formula. Don't memorize this formula. Don't think of it as a formula. Understand the concepts. Okay, so let's do an example as a refresher. So, refresher. 304 and let's say 5, 1, 2, and let's pretend that's a column vector. I'll put T here for transpose. We'll talk about that in a little bit. We should do it properly the first time. So 5, 0, 5, 1, 3. Okay. So when I multiply v and w, I should get 3, 0, 4, 5, 1, 3, and this is going to give me 3 times 5 plus 0 times 1 plus 4 times 3. So this is going to be 15 and 12, whatever that is, 27. Okay, so that's how you multiplied a pair of rows and columns. A single row and a single column. Okay, so let's think about a matrix. What is a matrix? Well, it's a table. So it's a collection of rows and columns. And so defining matrix multiplication is just going to reduce to using your definition for rows and columns. Okay, so I'm going to pull the example from the book because it looks kind of abstract, but I'm going to show you that it actually makes sense. And then we'll do an example with actual numbers. So here we have A11, and it's going all the way up to A1P. And now we're going down to the ith row, AI1, and then we're going over to AIP. So P is the number of columns. And it goes down to AM1, and it's going to end at AMP. Okay, so as a quick quiz, what is the dimension of A? Well, the dimension of A is, it's got M many rows, so it's M by P. Okay, so the next thing is they give us a matrix B, and B is going to have n many columns, and it's going to have P many rows. So that's BP1, and we're going to go over to BPJ, and our final element is BPN. Okay, so what's the size or the dimension of this guy? Well, the dimension of B, so this is the dimension of A, this is the dimension of B. The dimension of B is going to be P by N. Okay, so one way to think of, or one way to write this neater is to say that the dimension of A is MP. Now, this isn't referring to an entry because I'm using capital A and I'm not using a lowercase letter. And B, I'm gonna write it like this. Now, here's a rule that you have to learn right now, and that is that these inner dimensions have to be the same. What do I mean by inner dimension? I mean the number, the pair of numbers that are small and closest to the letter B, right? That pair right there. They have to be the same thing. And if they're not, your multiplication isn't defined. So maybe that's a little confusing. Let me give you a quick example of a pair of matrices whose product is not defined. Okay, so we need those inner dimensions to not match. So how about 3, 1, and so what size is this? This is 2 by 1, and so I'm gonna want to use a different, how about another one? How about another 2 by 1? Okay, so if this is A and this is B, because A has size 2, 1 and B has size 2, 1, notice that 1 and 2 do not match. Therefore, we cannot multiply them. Even though we could add them, right? If we added them, we'd get 5 for the first entry. So if I add them, right, then I would get 5, 4, right? But we're not adding them. We want to know if we can multiply them. And the answer is you cannot multiply them because these inner dimensions don't match. Okay, so let's get back to this very general example. So whenever we multiply a pair of matrices, the dimension of the dimension of AB, the new matrix that comes out that we're going to get from this product, right? The whole thing, AB, after we do all the calculation, its dimension is going to be M by N. M by N. And again, it's only defined if those inner dimensions match. Okay, so how do I find any given entry, right? So how do I find um, you know, if I denote, let's say we call A B C. Okay, so I'm going to say C is AB. How do I find C I J? Right? It's not exactly clear, but in fact, what you do is you pick out the ith row from the first matrix and the jth column from the second one. And because we know how to multiply vectors, these are both vectors. The first one's a row vector, the second one's a column vector, and we know exactly what that is. So what you literally do is you multiply AI1 and B1I or B1J, you multiply them and then you just keep adding, right? So that's pretty much it. So this would be AI1 B1J plus AI2 times B2J. And it's just going to keep going. And at the end, you multiply AIP and BPJ. Okay, so the neat thing about this is there are exactly, if you think about it, if you take a moment and think about it, doing multiplication like this will give you exactly m times n many entries, which is exactly what you need for you to have the dimension of AB be m by n. So let's go ahead and do a concrete example, since that's probably a little confusing, more than a little confusing perhaps. Okay, so here is a 2 by 2 matrix. Sometimes we like to write the number at the bottom right of the matrix. So what kind of matrix could we multiply this by? Well, because the second entry is 2, the new one is going to have 2 on the first entry. So that means it's going to have to have 2 rows. But the second one can be anything. So let's go ahead and make it 3. So I'm going to give this these entries so that our math is easy. And let's change the color. Okay. So suppose I say that I want to know what C22 is. Okay, C22. So the neat thing about this is that the first element always corresponds to the first matrix. And the second element always corresponds to the second matrix. Also, with the first matrix, you're only going to take rows, and with the second one, you're only going to take columns. So now we look at the number. This is a 2. So I'm going to go to the second row of the first matrix. And I'm going to go to the second column of the second matrix. I'm going to multiply those together, and this is just going to give me 4, right? So 3 times 0 plus 4 times 1, that's 4. Okay, so let's do another example. what about C1, 3? So if you're wondering how I'm getting these, I'm just I just haven't filled it in yet. So these are all the entries that are possible. Because remember, the new matrix picks up the dimension of the outside elements. So that would be 2, 3. So there's going to be 2 rows and 3 columns. Okay, so let's focus on this entry. So the first entry here is 1. So that tells us that in our first matrix, we're going to look at the first row. And in our second matrix, we're going to look at the third column. And when I multiply those together, I should get 2 times 1 plus 1 times 0. Again, if this doesn't make sense, you need to go back and review how to multiply matrices. Okay, so that's going to be it for the basic multiplication. In the next video, we're going to discuss setting up systems of equations and representing them as a matrix. Bye.